Let's see. Okay, I think they're there now. Okay. So solutions to quiz 7 are up there. I'm in the middle of grading, so some of you already can see your grades. I'm like halfway. I'm planning to finish, as usual, by Thursday, like about a week after it's due. Remember that the plan for now is section H of the combinatorics book. I'll tell you exactly. Today, it will be clear what is due this weekend. So for everybody, there is like the first part due this weekend and then the second part the following weekend. I'm really not grading or anything. I'm correcting, I'm editing that first part because it's necessary for the second part. And if that first part is wrong, then the second part is going to be wrong. So you still have time. Let's say if there are mistakes, that's the idea. It's due this weekend so that if there are mistakes, I have time to correct everybody's work and you can go to the second part. And that's when, for the next weekend is when it's supposed to, not the next weekend, sorry, the Wednesday, before our last class next week, so that we can go over any questions before, during our last meeting. So, I'll tell you what everything is about today, and hopefully that will clarify things. Now, just one note, I made a mistake for the assignment of the first 3 problems. So if you already took a look at the problems assigned for section H, for this last section, for the first 3 groups, I had problems 50, 51, and 57. 57 wasn't much of an issue, but 50 and 51 don't really fit my plan of having those two stages of the problem. And so I changed them to 54, 55, and 58. So those 3 problems that are about the strings, they wouldn't really fit the plan as for all the other problems. So that was my mistake. I thought I was selecting different problems. So just be aware that I changed those 3. I made a note, so it should be clear, but I just wanted to make sure you knew. Now, one more thing. Office hours this week, I have an hour and a half today instead of 45 minutes Tuesday and Thursday. I have one of my students graduating, so I've been working with him, and I think I'm going to need some time to finish up with some other things. I think it's going to work better to have longer office hours just today. Okay, so today office hours. Oh, let me start sharing. So I'll write it down here. This week's office hours, I'll be there. I can stay even a little bit longer if, as usual, I. But so let me say office hours this week. If you need to see me, after today because you're working on your problem, that's fine. We can find another time, but I cannot make the usual time. So it's going to be Tuesday. So today, 4 to 5:30. And on Thursday, I don't have office hours. But if you need to see me, just let me know. Okay, we can find some other time. I just cannot make the usual time. Okay. All right. So let me summarize what this section is about. Oh, before that, any questions? I think there's something. Oh no, good morning. Thank you, Ramsey. Good morning.
But next week hours gonna hours gonna stay the same, right?
Yes.
Okay.
Yeah, and actually, because the problem is due Wednesday, you might need to see me earlier rather than on Thursday, or maybe Thursday because of the midterm. I can expand office hours. It's okay. I know that as finals, in our case, our last midterm and last assignment you might need more help. So I can expand office hours. I have the regular ones, and also let me know if you need to see me at a different time.
Okay, so our assignment is gonna be due on 8th, the first one, right? Which is Saturday.
The first one.
I see.
Yeah,
Okay.
it's a Saturday, so that I have time to correct it for you, so that you can make you can go to the second part. So wikis. So those are the wikis on section H of the combinatorics book. And again, I'll explain today what I mean by that first stage, second stage. So I'll call it first draft. What about it? So first draft due 5/8 is this Saturday. So I can spend Sunday and Monday making edits to those. So on Tuesday when we see each other, I finish clarifying what's missing for those problems, and we have some more examples, and then the final draft uh, is due on the 12th. That's a Wednesday. So that on Thursday we can go over any questions. We can go kind of like a review for that midterm, and then I'll make sure that I correct that final draft for all the wikis, by the weekend, so that you have time to go over them before the midterm. The midterm is on the 18th.
So, question though, will like the homework problems, like the soccer ball problem or the H36 or H37 problems, we go over during the lecture today, or will that be in office hours?
Let's do this, Sean. Let me go over the material that I need to for today, and maybe we can spend some time on Thursday for the planarity, so that the groups working together on this new section H have material to get started today. So maybe on Thursday we can spend a little more time. If you feel like you need a lot more time, then just come to my office hours, set up an appointment. Okay?
Okay. Maybe then I'll ask you any questions I have during lecture today. I'll ask you in office hours, and if I have a little more time to do that, then I will ask about the homework problems for the quiz from the quiz.
Perfect, Sean. That's a good plan.
Thank
Okay. Both books, right? Sections H in both books. That's the third midterm, and that's on the 18th. And the times are different. I don't remember exactly, but they're in the syllabus, and then they're in Canvas, and then I'll remind you as time gets closer. All right. Any other questions?
Will we review for the exam 3 as you did it for exam 2?
Yes, we'll do that on the last Thursday that we meet. So next week, Thursday next week. Anything else? Right. Okay. So let me tell you what this section is about. I recommend you to have colors handy. It's not a joke. We're coloring objects, so it's good to have colors. Um, this is again section H. Is Polia's field. I always call it Polia's method, but I should probably use both names. Okay, so we're counting something. So I'll give you the most general problem that we're trying to solve, and then I'm going to give you different variations of that problem. So the problem is like this. How many colorings? And here you're going to have some object. Yeah. So I'll fill in the blank with different possibilities so that you see different problems. How many colorings of a certain object are there using um, a certain number of colors? So, using, let me call it right now, K colors that varies in the problem. If, oh, and here we're going to have some transformations of a coloring are considered the same. I know it doesn't make sense right now, but once we fill in the blanks, it will make sense. Are considered the same. And then sometimes you have an extra. Sometimes the problem just ends right there, but sometimes you have an extra condition about, something like all the colors need to be used exactly a number of times, but I'll also list some examples of extra conditions. Okay. So that's kind of the most general problem. So let me, let's try to fill in the blanks with the specific examples so that you actually see a specific problem. So first, let me tell you what kind of objects are we talking about? Uh-huh. What kind of transformations? Actually, you know what? Let me list them below. Objects, transformations, and extra conditions. Okay, so I'll give you examples of each of those three things. Um, Objects. We can color. We're gonna use. Actually, you know what? Sorry, guys. Let me give you an alternate version of this problem because it's for those three problems for the first three groups. We're gonna work with the strings with words. So this is an equivalent type of problem. This is gonna be how many words. Actually, let me say again. All of this will be clearer soon. So cyclic words are there, or actually, let me say circular. These are my colorings. So this is like my colorings. I'll explain. That's what takes the place of the colorings. Um, Using some set of letters, using A, B, and C. That's gonna be my colors. That's what takes the place of the colors. Here, sometimes instead of saying three colors, you're told use red, blue, and green. Here you're going to be told use letters A, B, and C. Again, I'll give you examples. If rotations of a word are considered the same. So this is like a special case, but it comes up very often in this chapter. Those are the transformations. Again, sometimes you have extra conditions, just like each letter needs to be used at least once, or the there must be two A's in the word, or something like that. Okay. So now let me give you. I guess I'll give you a specific example, and then I'll give you, different types of objects that you can use, different types of transformations, and etc. So
Do we have two colorings in this example? This problem?
yes, we could have colorings just using two colors, right? So two colorings. That would be. Let me give you an example, and then maybe I'm not understanding your question also. So let me give you an example, and then you ask me again. Okay.
Okay, I was
So-
just wondering, is words supposed to be objects, or is that also colorings?
Oh, I see. I see. I see what you're saying. Okay, let me say colorings of the objects. So yes, so the words already have the letters in them, right? So which means is that you can think of the word as spots for the letters, like a circle, and you're going to decide the letters in that circle. So the letters are the colors, and the actual word is already the colored object. So, but maybe with the examples, it will be clearer. Okay, so let me go over a generic, over an example of this generic problem, and then I'll give you an example that's equivalent in this setting. And then maybe we'll clarify things. Mhm. So actually, let me copy paste this and just fill in the blanks so that you see, so that you see that it's actually one of these problems. Okay, so an example of this could be how many colorings of, let me just remove this. So how many colorings of the vertices of a square, let's say? I will do it in black. Oops. So that's my first blank, right? How many colorings of the vertices of a square are there using two colors? Or I can even be more specific with red and blue. Sometimes you are actually given the colors to be used. Sometimes you're just told two colors. If all I'm here for my transformations, I'm going to use rotations. If all rotations of a coloring are considered the same. And no extra conditions this time because it's my first example, right? So I'm just going to remove this. No extra conditions. Okay? So how many colorings of the vertex of the square are there using red and blue if all rotations of a coloring are considered the same? So what does this mean? Well, I have a square. So let's see if I can draw a square. No, I want a perfect square. Let's see. Okay, so there. How many colorings of the vertex of the square? I'm just going to duplicate this. Are there using red and blue if rotations are considered the same? So what do I mean by that? Well, this is a coloring. This is a coloring of the vertices of the square with red and blue, right? Well, this one and any rotation of it. So if you take that one and rotate it 90 degrees clockwise or counterclockwise, by the way, it will give you the same. But if you rotate it, let's say counterclockwise, then, if you rotate these 90 degrees, then you're going to get the blue here. This blue is going to go there. And then this is that red goes here, and then blue, and then red. You see? Mhm. So I'm gonna just label them to indicate that I'm actually rotating, but the labels don't matter. Okay, this is just to indicate that I'm rotating it so that you can see that we actually, did something. 1, 2, 3, 4. So I'm actually rotating. So this is 1, 2, 3, 4. You see, we rotated 90 degrees, and then you can rotate again, and oops, I need another one. So you can rotate again another 90 degrees, or you see, or if I take this one and I rotate it, the original one I rotated 180 degrees, then um, I will get actually the same coloring as the original one. It looks exactly the same, but now if I were to label my vertices, then this one will be 1, 2, 3, and 4. So like another 90 degrees, and then another 90 degrees. So this one right here. So if I do 90 degrees one more time, those will be blue, this will be red, and this is my um, 1, 2, 3, 4. So again, labels are not important. This is so that you see that I'm actually, rotating. But you see, all of these are considered the same. Rotations of what coloring are considered the same. Or maybe I'll say all these are considered the same. All of this. Huh? And you can see that if I remove the labels, the first and the third are really, really, really the same. They look exactly the same. But the first and the second, you need to move something to make them look exactly the same in the same position. But what we're saying is that all of those are the same. Okay? Makes sense? So we want to count how many different ways, right? So since all of these are considered the same, let's see. So how many ways? So if those are considered the same, how many different colorings are there? And with such a small problem, maybe you can actually try them all. I can have all vertices of the same color. That's one way. I'm gonna make more copies of that. You can have the other color, right? All of the vertices are the other color. In fact, I'm gonna move this one here because there is some kind of equivalence of duality here. So all red, or I can have 3 blue and 1 red. And here's the thing: does it matter where the red is?
No.
No, because the rotations. See, if I place the red someplace else, it's going to be a rotation of this one, and we say that all the rotations are considered the same, right? So it doesn't matter where it is. And so just so that I'm carefully counting, I'm just going to consider the other possibility of having 1 blue and 3 red. Mhm. And then I can have 2 of each color. So I can have 2 of each color, and I can have them, let's see, I can have them maybe like consecutive ones. The red ones are consecutive and blue ones are consecutive. And again, I have all the rotations. I could have the 2 red ones on the right side and it's equivalent to this one, or on the left and it's equivalent to that one. Okay? Or and there's no clue. You see, if I do what I've been doing, like now make this one's red and this one's blue. You see, I've been kind of switching the colors here. Those two will be equivalent. So I just have that one. Mhm. And I can also have the blues and the reds alternating. Those are definitely different, right? Because I cannot go with rotations from one to the other. And that's it. There's only 6. You see?
Is there going to be like a formula or something to get the answer
Yes.
quicker?
Yeah. So we're gonna learn how to do this in a more general way. Because for colorings of these 4 vertices it's kind of easy. If you had more colors, then you have to be more careful. If I told you, what if there are 10 colors available? Then you have to be careful. Like then I could do this with any of the 10 colors, and then I could do this with any pair of colors, and then I can do this. It's related to this one, but it's not the same problem if I change the number of colors. Mhm. But what's going to be important is to kind of identify these 6, or actually these 4 if you want. It's important to identify these 4 in order to solve the problem for any number of colors. Here's what I mean by this. Let me move this too. Or maybe I'll leave them. I'll just leave them there. So my answer for that one is 6. What should I do now? Oh, okay. So what if I change the number of colors? So what if I take this problem, this same problem, but I change the number of colors, right? So I'm just gonna move that over here. So what if we only change the number of colors? So this time, instead of this, I'm just going to change these 2 to 10, let's say. Okay, everything else remains the same. Okay, and so here's the thing. As long as I know, we still need to count like we did here, right? Right now we don't have any method, but we need to count the same way that we did here. We will say, okay, if I only use one color, then it looks like this. But that color could be blue or could be red or could be any of the 10 colors, right? So this column will actually have 10 copies, one blue, one red, one green, one of each of the 10 colors. Make sense? And then if what, let me remove this because I think it is distracting. So if I have 10 colors, but everything else is the same. So regardless of the number of colors, so far, these ones tell me part of this problem. So if I only use one color at a time, for the entire figure, then I'm going to have 10 colors. So this one is associated 10 different colors, one for each color. This one is just me using 2 of the colors. It could use any 2 of the 10 available colors, right? And so I don't know. Maybe I'll do it here. So I need to be more careful using one of the 10 colors. So I can, just give this as an example. And there's going to be 10 of these, one like this per color. 10. And then I can also have, using 2 colors. Well, I'm gonna have like all these possibilities, like these possibilities. Huh? So if I'm using two colors, I can have this, one of the points being one color and the other three the other color, or I can have two of each consecutive like that, or I can have um, two of each like this. Mhm. And then I need to see in how many ways I can do this if I have 10 colors available. Uh-huh. So for each two colors, okay. So, if I have blue and red, I can have this one, or I can have this one right here. This one right here. Uh-huh. So if you give me two colors, we kind of already did it. If I had two colors, then this one becomes two of them. I can use one of the colors for the 3 points and then the other for the point by itself, or I can switch. So this one actually becomes two of those. But the others, because of the symmetries, because of the rotation, because rotations are the same, this only, if you just give me two colors, I have a unique way to do this. I have a unique way to do that, right? So this gives me four for any pair. Four, uh, actually, four for each pair of colors, right? And how many pairs of colors I have? I've takes two pairs of colors times four. Mhm. And then we need to count the ones using 3 of the 10 colors. And then I need to use the ones using 4 of the 10 colors. And that's it, right? Because since I'm only coloring 4 vertices, I cannot use 5 colors at the same time. So I will need to do that. And for each one of those, I need to do some work. But the importance of this method that we're going to learn is that we can cover all of these problems at once. And we can cover all of this if we change, if we just leave the vertices of the square fixed. Let me go back to my problem. So if I just leave the vertices of the square here and rotations fixed here, then I can have any number of colors here and lots of different conditions here, and the method will solve all of those problems essentially at once. So that's the goal of this section. Solving all these types of problems, due to kind of the hard work, which is going to be related to finding these like basic ways of coloring, and then you can apply that. We're gonna actually get 3 polynomials. Those 3 polynomials are gonna give us essentially all of our answers to all these problems, whether you change the number of colors or you change the conditions. Okay, and of course I need to tell you what kind of conditions I'm talking about. Make sense? So that's our goal. Having a method to do this rather than doing this by hand every single time. You can see that it can be very time consuming, but the method will give us an answer to this. A very easy way to get answers to all these problems at the same time. Mm-hmm. So I didn't finish this one. If I have time next time, we'll finish it. But I'd rather go into the method. Mm-hmm. Now, let me go back, and I told you I was going to clarify this other version of the problem, right? So let me do that. I'm gonna copy paste this one, and I'm actually going to relate it to the one that we just did with the square. So I'm gonna give you a problem that's equivalent to the square problem, but with words. Okay? So here it is. I'll put them back to back again so that you can compare them. But it's how many words So this circular, I'll explain why it's there, but how many words are there using? And so here, instead of some letters of the alphabet, I'm just going to say that's like the colors, right? So using A's and B's. So that's like my two colors, A and B. If I'm going to use rotations as my transformation, if rotations of a word are considered the same and no extra conditions. Okay, so these are my colors. Again, these words are the colorings of my objects. Mhm. So maybe I shouldn't. That's always the context for this second type of problem. But I have words and rotations. Okay, so let me tell you what we mean by this. We're considering words, but I put circular in parentheses because a typical word just by itself, with using A's and B's, would look like this, right? So that's just word. That's just the word. When I say, if you think about the words as circular, you can think of that one as, being in a circle. A, B, B, A. Make sense? Or, I drew the circle, but think about it as being positioned in a circular way. Mhm. So instead of a linear, let's say, I'm just going to write here linear word versus a circular word. Make sense? So maybe like this. Uh-huh. So we're actually counting, think about it as counting circular words. Think about A and B as the colors, and rotations of those rotations are considered the same, right? Rotations of the word are considered the same. It means the following. I had the ABBA, which in the circle looks like this. A, B, A, no, sorry, A, B, B, A, like this, right? But then I can apply a rotation to my word, and then I get this A goes here, the other A, the B, and the B. You see, I rotate 90 degrees, and I get that one. Yeah, and if I rotate again, I get B, B, A, A. I get this one. And if I rotate again, I get, did I do this correctly? I didn't do this correctly. Wait.
I think there's still a B on the top.
Yes, there's still a B on the top. So my A is just move one position, my B's, thank you. Yeah, like that. And then I rotate. So I'm kind of following this A if you want. The first A, it was on top, left, bottom, and now it's going to be on the right. My first A, right? Well, I don't know. I should probably be following my really first letter in the word of the. I need to do this. So instead of underlining that one, let me underline this one right here, right? So A, B, B, A, A, B, B, A, A, B, B, A, A, B, B, A. And I'm looking at them counterclockwise, right? So look, even though we're talking about words, when we say that rotations are equivalent, we're thinking about them positioned in a circle. So this second word actually becomes a this other word becomes I want to say BB. Should I have done the other rotation? Sorry, guys. What about this? I'm gonna change my. Sorry, guys. I just wanted to go with my words here. B B A A. And so I think I'm gonna have to change. A. Okay, so sorry guys, I just want my pictures to go with my words above, and I want that to match the order in which the book tells you the rotations of the word happen. So I'm going to label this again. So here we go. Sorry about that, but I think it's better to correct it here so that it's easy to go from this, the circular diagrams to the words to the way that the order in which the book gives you the rotations. So instead of rotating counterclockwise, I'm going to rotate clockwise. So here we go. So I'm actually going to start with oh, you know what? Let me just make sure. Oh, this is fine. Sorry, I hope you didn't remove it. So here it is. So this is fine, but I'm gonna read my words. I'm gonna read my words clockwise, starting from the only thing that I'm going to change is which A I'm underlining. Okay. I'm going to underline this one. Anyways, this is the one that I was underlining. So I haven't changed anything. Okay, I haven't changed anything, but I'm gonna read my words starting here, starting at top, and then I'm gonna read them clockwise. You see, so to make the connection with my words here. So here I have A B B A B B A. Is this one, and now here I have B B A. Make sense? So I'm going clockwise when I read them. So this one is going to go with B, B, A, A. Again, I'm starting with this B, with whatever letter I have on top. And then I'm reading my word in this direction. Okay, so B, B, A, A. And then I'm going to read this one, B, A, A, B. B, A, A, B. And then I'm going to read this one, A, A, B, B. Oops.
Professor, I have a question.
Yeah.
Shouldn't the underlined A be the one on the top for the last graph or for the last circle?
Oh, thank you. So I think I had it like that at the beginning, huh? I shouldn't have erased anything. Thank you. Yeah. Just as a reference, again, those little marks are just so you know what I'm doing here. I started like this, just underline whichever you want, just one of them, and start rotating, right? So I decided to underline that one, and then you just rotate. So 90, and then 90, and then 90, and if you rotate again, you're back to that one. So imagine you're just rotating. So once you have all of this, I can read my words just, starting at the same place. So here I have A, B, B, A, B, B, A, A, B, A, A, B, A, A, B, B. So it's these words here.
Professor,
all of these are considered the same.
I have another question.
Yeah.
If you had more than 4 letters, it wouldn't be 90 degrees, right?
It wouldn't be 90 degrees. Just Take
Are
it
we
to the next.
supposed to know what the degrees are, or does that not matter with these kinds of problems?
It doesn't matter, but if you have more, it would be if you have K letters, right? Or maybe I shouldn't say K letters because it's also the number of letters that you're using. I don't know all that. But if this is words of length n, right? These are words of length 4. So if you have words of length n, then the 90 degrees becomes 360 divided by n. That would be the angle of rotation. The smallest angle of rotation to take one about it. Yeah. And so the way the book presents these rotations so that you don't have these diagrams, but I think you should think about the words as being circular, is, when you apply one rotation, so from here to here, you're applying what they call R1. And what it means is that you take one letter and just move it to the end. And then you will have the word BBA and the A that you move to the end. Make sense? And so this one from here to here, it's called R2, which means that you take the first two letters, and move them to the end. So in this case, it would be AB is moved to the end, AB.
Question.
Mm-hmm.
Regarding these things, the diagram, like, I'm having a hard time figuring out BAAB is this diagram, because if I start with the one that's underlined, so this A is this A, followed by B, B, then A again. But then if I start with this underlined here, it starts with a B though here, so I'm a little confused about that part.
So again, to read them, you start here
On the top.
Yeah, I start here and go clockwise.
I go clockwise. Shouldn't it be BBAA, which is here,
Yeah.
but that's not associated with this diagram here.
It is, right? So I start right here. That's my B. And then I go clockwise. A, and B.
Oh, clockwise. I was looking counterclockwise. Never mind.
Yeah. So we rotated counterclockwise to draw the diagrams, but then we read them clockwise. It doesn't matter as much. You'll see, Sean, that.
Okay, because I was a little confused because when you did the rotating part of 90 degrees, that's counterclockwise, right?
That's counterclockwise. But then to read them, we read them starting here on top and then clockwise. But again, it doesn't matter as much. And that's why I was kind of struggling getting it right so that it goes with the book. You see, in the book, they define rotations as taking the initial segment of a word and just moving it to the end. Mm-hmm. But you could also take the ending part of the word and placing it at the beginning. And it's just whether you're rotating one way or the other. So that's why it's not terribly important. Don't stress too much about it right now. Once we get to the method, you'll see that it's not going to matter.
Okay. Oh, I already know somewhat of this stuff because I have to deal with Math 360, reflections, rotations, and S3, and dihedral groups and stuff like that.
Yeah. So we're going to use that, although we're not going to call it that because that's not a prerequisite for this class, but I'm going to try to relate to that class in case you've taken. Okay? So, look, I zoom out. I know it's very tiny, but I just want you to see that, that was for, I guess, that was my problem with the squares, and this is my problem with words, right? And so I just want you to see that it will be essentially the same because, coloring the vertices of a square or coloring 4 points along a circle is essentially the same thing. In fact, let me just to make the connection a little bit better. Think of that word A, AABB. You can think about it as AABB. There's my underline. And it doesn't really matter which one, just one position. And then you have, I should have copied that one before. And so you have this other one. So what did I do? I did the starting on top. So I could have B, A, B, and I can have B, B, A. And then I can have A, B, B, A. Which corresponds to maybe all the B's are blues. And all the A's are reds. And you can see that we're just saying that the rotations of a coloring are considered the same. And so solving the problem with two colors or solving this word problem, it's exactly the same. The answer to this problem is also 6. Same as in the square. But when you talk about rotations, the way that they are presented in the book, rotations of a word are actually what I was telling you here. So let me go over here. So when you're talking about rotations of a word, I have A, that's one possibility, right? And if I apply any rotation, it gets me to the same word. So it's just that one. And then I can have A's and a B someplace. But that's equivalent to, again, my rotations in words are, you just take the first letter and move it to the end, right? That's like the smallest rotation. That's like the 90 degrees rotation for us in the square. So it would be A, B, B. And then again, I take this one and I move it to the end. And it gives me A, B, B, A. Sorry. A. What did I do? Wait. So
yeah, how did we go from A, B to A?
Yeah.
I think it was supposed to be A at the end, right?
I know you're absolutely right. So I was just moving that A. I was just moving the. I kind of got stuck in my 2 A's and 2 B's. So I just take that A and move it to the end, right? So do we agree now?
Yeah, I got you. Yeah, that makes sense.
Thank you. And so take again the first letter, move it to the end. So I have the ABA, and then my first letter was moved to the end, right? And then same thing again. I take the last letter, move it to the end, so I get the BAAA. And then if I do it again, take that last letter and put it on the end, then that brings me back to that one. So this is an orbit. These are the orbits. If you've taken 360, these are the orbits in my group. So I also have the, 2 A's and 2 B's. So I have AA, they can be like consecutive, AA, BB, and then take the first letter, move it to the end, A, B, B, A. Take first letter, move it to the end, B, B, A, A. Take the first letter, move it to the end, B, A, A, B. And then back to A, A, B, B. Take the first letter, move it to the end, you go back to A, A, B, B. Or I could also have 2 of each, but alternating. Take the first letter, move it to the end, the AB, and then the A that was originally in first place. But then take the B, move it to the end, A, B, A, B. And I'm back already. You see? Those two are the same. So I shouldn't have written that one. Or maybe I should say, yeah. So you see, so I apply the rotation. I apply a rotation to this one. It just takes me to the same place. I apply a rotation to this one. It goes to BABA, and then it goes back to ABAB. Mm-hmm. And then what else do I have? Three B's and an A is just going to behave like three A's and a B. Mm-hmm. So then I have BBAB, BABB, ABBB, mm-hmm. And then back. If I move the A to the end, and I'm back to that word. And then I can have BBBB. So these are my 6 orbits. These are my colorings. This is the number of words. This is my solution. Number of words, number of colorings, number of orbits. Those are the orbits. And the number of orbits is 6. That's our answer. You see? So, and because, each one of these is considered the same because they are the same on the rotations, right? So I only have 6 different words or 6 different orbits. Make sense? Mm-hmm. Okay. So here's the thing. We want to find what is called the pattern that helps me figure out how many of these orbits I have. So let me tell you what I mean by that. If I want to have one of these orbits that only has a single element, meaning I start with the A, and I apply one of my rotations, and I get here to the same thing. I apply another rotation. I get. This is a fixed element. Mm-hmm. If I want to find all of the words that satisfy this, or if I want to find all of the words whose orbit has length 4, or all the words whose orbit has length 2, there are some things that I can do. I can find what is called a pattern. The pattern for my transformations. Okay, so before I go into that, let me ask you if there are any questions so far.
Professor, just one question.
Mm-hmm. Mm-hmm.
How were we able to tell the language rule before? Is it the hint we got it from the circular words, or because
the length of the orbit?
Yes. I'm just wondering, why are we looking at cases where length is 4 with this problem?
Oh, here's the thing. If you wanted to compute how many words, let's focus on the word problem for a minute, right? If you just wanted to know how many words are there and there is no restriction in terms of the rotations, then it's very easy to count, right? Because you have 2 possibilities for each position, so you will have 16. So if you forget about the rotations part of it, you have 16 words. And here I have the 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But those 16s are in equivalence classes. So here you have all your words. These ones are length 4 using 2 letters A and B. So that's kind of your universe. And they have equivalence classes. The equivalence classes are the orbits. So the orbits are the equivalence classes. Rotation equivalence classes. So if there is a rotation that takes one word into another, then they're considered the same. So I'm going to have the VVVV by itself, the AAAA by itself, and then I have the BABA and ABAB as another one. And then I have these other two that have I need three more. So I'm gonna have the ones of the four elements, right? The AAA, B, AABA, ABAA, and BAAA. So, and then I have the other two, right? So that's really what we're doing. So the idea in the method that we're going to use is that it's easy to count how many ways you have total. And we need to understand how these things group into equivalence classes. Mm-hmm. And so that has to do with the symmetries. In this case, this has to do with the symmetries of the square, mm-hmm. with the rotational symmetries of the square. And this, in terms of words, it has to do with the length, whether the length of the orbit, the length of the orbit always divides the length of the word. So you're only going to have orbits of size 1, orbits of size 4, and orbits of size 2 in this case. But if you have words of length 12, you can have orbits of lengths 1, 2, 3, 4, 6, and 12, divisors of 12. So we'll get a little bit more into that when we, let me give you the general setup for the method, and then we'll come back and see how we can solve this particular problem in general. So the one for words. But I really want to focus in the general problem. Remember that this is just one possible interpretation or one possible equivalent setting to our general problem. Our general problem is this one right here. And I just made kind of the translation into words, but we really want to learn how to solve this one, because if we know how to solve this one, we'll know how to solve this one as well. And we can make the translation again at that time. Okay? So let me do two things in the last 10 minutes. I'm going to tell you the type of objects, transformations, and extra conditions that you can have. And then I'll tell you how that relates to your homework. We'll do the patterns next time, which is what you need to do in your first draft of the homework. So here, what kind of objects can you have? Well, I already told you about the vertices of a square. Okay. So you can have, for example, vertices of a square, coloring the vertices of a square. And the solution to my problem, it's going to be the same if I don't change anything else, but just the object. Is going to be the same as coloring the edges of the square, because they have the same rotations. So if you go back and look at the same problem, but instead of coloring the vertices, color the edges, you'll see that you'll also get the answer 6. Mm-hmm. And there is a one-to-one correspondence between the colorings. So the edges or sides of the square, right? Which is equivalent to words of length 4. So I showed you. And it's also equivalent to the 2x2 grid. So, imagine that you have, or a 2x2 board, I guess. So imagine that now you want to color these little squares, with blue and red. Oh. So this will be the one where the corners have blue, and the other two corners, the opposite corners, had blue and red. You can see that there is a one-to-one correspondence between these and coloring the vertices of a square like that. Or coloring the sides of a square like this. Or the word, as I was describing before, ABAB. See, so all of these problems are the same. Well, these families of objects. And if you want to do something more drastic, you can talk about coloring the vertices of a regular polygon with n sides. So I'm just going to call this the regular n-gon. So the regular n-gon, like a hexagon, that would be n equals 6. Or you can also color the sides of a regular n-gon. Or you can consider warps of length n. Yes, circular warps as we were using before. And for the board, it's not exactly the same, but instead of a 2x2 board, I could use necklaces or bracelets. Like the different colors around a necklace or a bracelet. That's another possibility. All of those problems are the same. You can also have as a different set of problems vertices of a cube, following these lines, vertices of a cube, edges of a cube, faces of a cube, the cells of a 3x3x3, let's say, cube, like the Rubik's Cube. Something like this, where you're actually coloring these little faces. So you have 36 things that you have to color. You can see how complicated this can get, but with the method, it is complicated, but not as much. Or, why not, if we're doing the cube, why not doing, vertices, edges, faces, and maybe also cells of some sort of a tetrahedron. Have you seen those, is the Rubik tetrahedra? For, maybe you have, maybe you have the tetrahedra and maybe you have little triangles there. Something like that. And there's also something on the back. Something like this. So you also would like to maybe color that, those little triangles in a tetrahedron. Or other polyhedra, the faces of a dodecahedron or something like that. Same idea, faces or vertices or edges, sometimes combinations of those. We're not going to combine them, but Or maybe circles forming a triangle, like, something like this, and you're coloring those circles. And again, rotations are considered the same, or spheres forming a pyramid. This time, I don't know. I don't know how to make this picture. These are supposed to be, maybe you have a sphere here on top or behind. I don't know. There's a nice picture in the book for that. But imagine 4 spheres, 3 on top of the table forming a triangle and another sphere on top. So in how many ways can you color those spheres if rotations in the space are considered the same? Mm-hmm. So there's a bunch of problems in the homework. You have word problems, like the strings, like this one. The first 3 are like words of length n. And then you also have like this, but for the 3 by 3, like this one. And then you also have the spheres ones. I think the last problem is on the spheres like this. And you also have for the cube, I think you have all different possibilities for the cube and also for the tetrahedron. So, you're going to see those. And then for transformations, the only ones that we're going to use are rotations and reflections. So the symmetric or dihedral groups. Although we're going to use this for the space as well, like for figures like this. We also have rotations and reflections, but in the space. And then for extra conditions, and I'll finish with this, and then we'll see how to solve them with the method next time, at least the first part of it. For the extra conditions, we have the, using each color at least once or twice or whatever, 3 times, whatever it is, using each color a certain number of times. So I can tell you, use each color exactly 3 times if there are 9 things that you need to color. Or I can tell you if there is like, these 9 circles, I can tell you 1 blue, 2 green, 3 red. How many ways can you do that? And we will be able to solve all of those variations at the same time, just by getting some patterns and 3 polynomials. And of course, we're going to figure out the coefficient of this polynomial is going to be the solution to this problem. So our goal is to get those 3 polynomials and understand what they mean. But in order to get to these 3 polynomials, we need to understand the rotations, the patterns, and that's what I'm going to talk about next time. So what you can start doing if you have time to meet with your group is just understanding the rotations or reflections of the figure that you got. If you got words, then it's just the circle, right? Like a regular polygon. You can think of a regular polygon. Or if it's words of length 8, it's a octagon. If you got the cube, think about the different rotations that the cube has. How many? Search for it. Rotations of the cube, reflections of the cube. Same for the tetrahedron if you got a pyramid or the spheres in that last problem, and so on. So you can start by doing that. Next time I told you how to find the patterns. And then on Tuesday, I told you how to find the polynomials and how to use them. All right? Okay, guys, thank you so much for your patience. I remember my office hours 4 to 5:30 today, in case you like to come. Thank you. Bye, everyone.
Thank you.
Thank
Bye.
you.